Hi, I'm Josephine. My topic is combinatorial circuits, and all of the information in this video is from chapter 11 of the textbook, mostly sections 11.1 and 11.5. So the basic idea of combinatorial circuits is that everything that happens in a computer uses bits, or the combinations of ones and zeros that we've learned about earlier in the semester. And this section discusses circuits and how they communicate by transmitting two different voltage levels that suggest ones and zeros. And honestly, while reading this section, I was a little confused when they were talking about real circuits or the more metaphorical math circuits, and when they were talking about voltage. So I'll probably talk about this as if it's just a mathematical idea from ones and zeros, or with ones and zeros from here on out. But I just wanted you to know that it really has to do with computers and how computers work. Anyway, here's a combinatorial circuit from the book, so you can just get an idea of what they look like. They are made up of these gates. These shapes are the gates. And basically we put inputs, ones and zeros, in this side. So we assign like maybe x1 equals 1 and x2 equals 0 and x3 equals 1. And then we see what these gates do to those inputs. We see what our output is, and our output will also equal a 1 or a 0. So I wanted to take a little bit of time to talk about these gates, the pieces that the circuits are made of. So there are three basic types of gates. This first one is called the AND gate. It has this sort of shape, kind of like half of an oval. And I've seen the shapes vary a little bit in different sources, but I think that's kind of the general shape. But it has two inputs, x1 and x2, which again can be assigned zeros and ones. And then the output is x1 and x2, and this symbol in the middle should look familiar from earlier in the semester. And then we can build a logic table, so again, similar to the truth tables from earlier in the semester, and basically investigate what happens with each combination of inputs. So for example, in this first line, if both x1 and x2 are 1, then the AND gate has an output of 1. If in either of these next two lines, if one of them is 1 and one's 0, the AND gate doesn't like that. It says, nope, that's 0. And of course, if both are 0, it also says, okay, that's a 0. So we can also think of AND gates as taking the minimum of the two inputs, which I thought was a really interesting idea. So the minimum of the 1 and 1 is 1, but if we only have one, that's a lot of ones, sorry. Or here we have no ones, then it can't find that 1 as the minimum to be the output. Then we have the OR gate. Again, this shape is a little inconsistent throughout different sources, and also I made it by pasting two different shapes together on my PowerPoint, so it's not perfect, but this is really similar to the AND gate. It takes two inputs and gives one output, and it has the same symbol that we saw earlier in the year. And again, we can make a truth table. So again, reading across the row, if both inputs are ones, it's just looking for 1, 1 to get a, I need to stop saying 1. I think you get it. We just want one of our two inputs to be a 1. So the only time that it gives a 0 as the output is when both inputs are 0. So again, there's this cool idea where for the OR gate, we can think of it as identifying the maximum of the two inputs. Had to make sure I got that right. The maximum of the two. And then our final simple gate is the NOT gate, which actually only has one input, which makes it a little different. It's this triangle shape with a little circle at the end of it. And then the notation is this bar above the input. And I think I created a line segment. So this notation didn't work out down here. I just wrote not X. Anyway, but all this does, really simple logic table here, So that if we give it a 1, it gives back a 0. If we give it a 0, it gives back a 1. So I just wanted to talk a little bit more about combinatorial circuits, give a few more basics before we move on. So we can combine these and, or, and not gates in different ways to make combinatorial circuits, like that one we saw a few slides back. And then here's a little bit of a simpler one from the book. And we can also create a logic table. I think I might have accidentally said truth table a time or two, but they're called logic tables in this section. Anyway, we can create a logic table for the entire combinatorial circuit. So not just for the individual gates anymore, but we can say, hey, this circuit has 3 inputs. So we can look at all the combinations of 1s and 0s that are possible for those inputs. And then we can see what the output will be each time. And we can do this by just following through the diagram. This took some practice for me, but for example, if it's 0, 0, 0, we say, okay, if we put a 0 and a 0 into an AND gate, we know from a couple slides back, it gives us a 0. So then this is an OR gate, and we have a 0 and a 0 going into that, which gives us a 0 as well. And then a 0 going into a NOT gate gives us a 1, which we can confirm down here, or if we're building the truth table ourselves, we can write it and hope that it's correct. But one cool thing about these combinatorial circuits is that they don't store memory at all. Like what has happened before, what the inputs have been before doesn't affect what the new inputs will be. But the outputs are uniquely defined, which just means that if we were to put in the same inputs twice, we'd get the same output both times. Basically, it's consistent. Some of the questions in the book ask, like, is this thing a combinatorial circuit? And sometimes they do really funky things that basically mean you don't know if you'll get the same output every time. Yeah, there are some funky examples of that where it just kind of loops around in weird ways. Anyway, we want to be able to expect these same outputs every time. That is a good thing. All right, and then another piece of all of this is Boolean expressions, which are basically the way we represent combinatorial circuits symbolically. So in this little example from the book, they basically wrote what each gate was doing symbolically along each step. And if you'll notice, this is the same example from the last slide. So first, we took x1 and x sub 2 into an AND gate. So they just wrote that here, x sub 1 and x sub 2. And then we had this OR gate, and that was taking what we just had, the x sub 1 and x sub 2 from right here, or x sub 3. So parenthesis placement is very important here. And then the NOT gate was the final thing. So we just throw that whole bar over the top of it. We knotted it, was I think the book's language. But then this final part is our Boolean expression. So yeah, that's all we did was, again, book language, followed the flow of the circuit. It's very descriptive, but just followed the bits through it. And we're just finding a way to write down what it does. So some problems in the book just give you a Boolean expression. You don't even see the circuit at all. And one cool thing about this is that we can directly use the Boolean expressions to create those logic tables. So some book problems have you do that as well. I personally really enjoyed the visual part of like following the numbers through the circuit. But this is also interesting. To plug our numbers into this, we have to know the order of operations, which the book didn't go into too much detail on, but they did say that parentheses come first, like respect the parentheses, and also that AND is evaluated before OR. So yeah. And then as far as book problems go, the first multiple problems are exactly what we just did over the course of a few slides. So they are asking for the Boolean expression for the whole circuit, and then also for you to write a logic table. So I hope that if you've been listening for the past couple minutes, you could nail those, or at least do a short review and then do well on them. Okay, so here's a fun idea with two new gates. So those three basic gates, the and, or, and not, are cool. They're cool, right? But we can also have these other gates. So NAND, and I didn't include pictures of these because it's just brain clutter at this point, right? All these similar looking shapes, and we're not going to put them into a circuit picture here, but we'll talk about them. So NAND means and not. It's like a little mashup of those words. And NOR means or and not. And the idea here is that the three simple gates, the and, the or, and the not, are called functionally complete, which means we can make any combinatorial circuit using those three gates. But apparently, it turns out that and not are functionally complete. So if we ignore OR gates, we don't use them all at all, we can still make any combinatorial circuit. Similarly, if we ignore AND gates and just use NOR, ORs and NOTs, we can also make any combinatorial circuit. That I just didn't quite believe this. Honestly, I don't know, it's really cool to me. And I thought the proof idea was really cool as well. So I included a little snippet of this. And the proof just argues, it makes its argument by showing how we can replace the gate we're not using with the ones we are. So for example, this is a combinatorial circuit using and not gates that's logically equivalent to an OR gate. So anywhere that we have an OR gate in a circuit, we could just replace it with this somehow. I'm not not confident on that process at this point, but potentially there's a way that we could use this idea to do what the OR would do. But maybe that doesn't make it the most convenient circuit, the fastest circuit. So we have this idea of a minimization problem, which is simplifying combinatorial circuits to find the best one. And we can follow this set of rules that's laid out in the book and do it by simplifying the Boolean expression. And it makes the circuit better. So for example, 51 NOT gates in a row is logically equivalent to one NOT gate. So if we had that kind of issue, I mean, maybe there's a reason to have a 51 in your combinatorial circuit. But if not, we can definitely make that, maybe saying better is a little rude, but we can minimize it. So that's all I had for this topic. Thank you for listening.